Right, so in this question, you can see here the string is of length L, okay, and that's the distance between A and B to begin with, okay, but the string is just slack, okay, it's not perfectly taut yet, okay, and then impulse of 40 Newton seconds is applied to particle B at this angle alpha. Now remember, when you do impulse, right, impulse that acts on a body results in a change of momentum. Okay, and that's what impulse is, isn't it? So we get a diagram to start with. Look at the before situation and the after. Okay, now before, you've got these particle A, 2 kilograms, particle B of 3 kilograms. Okay, and nothing's happening. Okay, they're both stationary. The after situation, well, they start to move, don't they? And it said immediately after the blow, the speed of particle A is 4 meters per second, right? So A now we know after is moving 4 meters per second. Okay, A of mass 2 kilograms, 4. But what's good is, of course, I know the direction it's going to be traveling in is in the direction of the string. Yeah, because it'll be pulled by that string. So immediately afterwards, that's the direction it's going in. So the speed of 4 meters per second is going in the direction of the spring. However, particle B, right, 3 kilograms, this will have two directions, or it'll be going at that angle, won't it, we see here, because that's the direction of the impulse, so B is going to be shooting off, isn't it, in this sort of direction, okay, shoot off in this direction, but don't forget A, as I said, A will just be moving horizontally just after that impulse, because it's being pulled by the string, that's the direction it's going in. So we can have 4 going this way, but with particle B, right, we need to consider its velocity in 2 components, horizontal and vertical. Okay. Now, you can call this anything, right? And you can call this anything, but we actually know this is also got to be 4. If you think about it, because this string is going to be taut, the horizontal velocity component here has to be the same as this horizontal component, because they're going at the same speed, the string connected and taut, right? So that's going to be 4. We don't know what this is, okay? But of course, the overall velocity here is given by what's happened with this impact, this impulse here. So what we'll do is, we remember, right? Because they're telling us the impulse, we remember impulse is change in momentum. That's so important, okay? That's what impulse is, okay? Change in momentum. Now, unfortunately, with this question, right, because they've given the impulse on an angle alpha, right, we need to consider the impulse in a horizontal sort of direction and vertical, okay, right, so horizontally and perpendicular to it, right. So if we first of all consider what happens horizontally, we can see what the change of momentum is horizontally, but we can also see what the impulse is horizontally. Now if we think about it, if the impulse is this here, well, horizontally, that we look at, and vertically, we've got to look at the components, haven't we? Right? I say vertically, obviously this is looking down, isn't it, on it, but perpendicular to this direction, isn't it? Perpendicular to this direction. So there will resolve in this direction, so it'll be 40 cos alpha, and here it'll be 40 sine alpha. Okay, this is the impulse resolved horizontally and perpendicular to it. So going in this direction then, 40 cos alpha will be the change of momentum. So let's look at the change of momentum. Well, the momentum of the whole system we need to look at, right? So momentum here will be mass times velocity, 3 times 4. Add then the momentum of this, which is 2 times 4. Okay? So that's the overall momentum we've got in this system here. Now the momentum before then, we look at the momentum we've got here, well this will be 2 times 0, because it stays still, plus then 3 times 0, because that stays still. So work this out. This becomes 12 plus 8 is 20, equals 40 cos alpha. Okay, so then cos alpha will equal 20 over 40, okay, which means cos alpha is equal to a half, and then cos minus 1, then you get 60 degrees, okay. So we know what alpha is. Now, we can resolve the impulse perpendicular as well. Okay, now perpendicular, if you remember from the sheet, it was 40 sine alpha. Momentum after will be then 3 times x, okay, plus then this, which is 2 times 0, because there's nothing going perpendicular. Remember, it's going in the direction of the string. Take away then the stuff before. Now we know perpendicular, there's just nothing there, isn't it? You can just put 0. So we've got 40 sine alpha, and of course we know now alpha is 60 degrees, equals 3x. So simplify all this, right? You end up having 40 times root 3 over 2 equals 3x. So that means then x becomes 20 root 3 over 3. Okay? Now this will help us, of course, with part B, because in part B it's saying calculate the magnitude and direction of velocity of B immediately after the blow. Well, if we look at object B, of course we know now what x is. We know this is 4. This is 20 root 3 over 3. Okay? And it's going at this angle here. So this theta. So the magnitude will be using Pythagoras. Will be Pythagoras, so this squared, 4 squared, plus then this squared. So work that out in your calculator, you get 12.22, right, meters per second. And then to get the angle theta, now remember the angle it projects off, the angle B projects at will be different to alpha. Okay, that's so important. It won't be the same as alpha. Okay, you might think it is because you think, oh, there's an impulse here, okay, in that direction, so B is going to shoot off in this direction. Well, not quite, because of course B is affected by the fact that it's pulling A, isn't it? Okay, it's attached to A, so you've got to think that even though the impulse is shooting in that direction, it is being pulled back, isn't it? So it's going to be a slightly different angle. Okay, and you get theta then by just doing tan theta equals 20 root 3 over 3 over 4, and if you work that out, you get theta to be 70.9 degrees.